Okay, let's start today's class. These are the topics for today. In topic 1, I want to show you more examples about section 1.7. Then we turn to study section 2.1. The first topic of chapter 2 is matrix operations. For matrices, we can perform summation, subtraction, a scalar times a matrix, and a matrix times a matrix, but no a matrix divided by another matrix. No this operation. Okay. The third topic, identity matrix. This matrix plays the role in matrix product as the number 1 in the real numbers, in the real number operations. Identity matrix times any matrix is that matrix. Okay, say identity matrix times a matrix A. The result is the matrix A, just like the number 1 in the real numbers. The fourth topic, take a transpose on a matrix, rotate a matrix. Before I present the topics, take a review about some key points. Okay. Number 1, if a vector is a linear combination of some other vectors, say v1, v2, vk, then we say that the vector v linearly depends on these k vectors. Otherwise, if you cannot write vector v as a linear combination of these k vectors, we say that vector v is linearly independent of the k vectors. Otherwise, we say that v is linearly independent of the k vectors of v1, v2, vk. So this is the definition of linearly dependent and linearly independent. This is for a single vector. Now, for a set of vectors, a set of vectors, say a set of k vectors is said to be a linearly independent set. What it means? The meaning is, if the vector equation x1 v1 plus x2 v2 plus xk vk is 0. This vector equation always has solutions. Say 0, 0, 0 is one solution. Okay. But the solution, we call it trivial solution. If this vector equation has only the trivial solution, then we say that this set is a linearly independent set. When a set is linearly independent, the vectors in the set is independent to each other. Otherwise, if this vector equation has non-trivial solution, then we say that the set, the given set, is said to be linearly dependent. It's a linearly dependent set. Linearly dependent set. When a set is a linearly dependent set, at least one of the vectors in the set linearly depends on the other vectors. Okay. This is a review about some key points. Okay, definitions. Now, topic 1. More examples. More examples. Let me show you more examples. Example 1. Let be given 4 vectors. V1, 1, negative 2.
Yeah, not bad. I think all my kills were bots, but what? The lecture's on in the background here.
What is on the background? Oh, I just found that I mute. Now I unmute. You didn't hear me, right? Okay, example 1. We are given 4 vectors.
So who's touching your food?
Pardon? Actually, this example is similar to homework problem. Okay, now questions. Okay, determine if the set of these 4 vectors is linearly independent. Let me answer this question first. Solution. To determine a set is linearly independent or not, go back to the definition. We need to solve. Solve this better equation. This is a linear system. Okay. Augmented matrix is first column V1, second column V2. Augmented matrix. -3, 6, 12, and then 0, 1, 1. Coefficient matrix. Actually, this is a linear system. Coefficient matrix, and then right hand side 0, 0, 0. Now I reduce this linear system, this matrix to epsilon form. Let me see. No, I pick a wrong. I pick a wrong example.
Yeah, it's legal in every state surrounding us. It's what are you guys waiting for?
This example, I present this example in the last class. This one.
Bro, ranchers love driving around the rock.
Hey, I can hear you talking. Please mute, okay? Yeah, this example is similar to the homework.
Dude, Montana in the first day of having it legalized made $2 million.
Hey, pardon? I can hear you talk. Please mute. Okay, now the coefficient matrix is, let me change it. And here, free x 0. Then okay, the first column is a 1, -3, 2, then -3, 9, -6, and then 5, -7, h. Okay, now determine if sorry, the first question is not this question. No, I'm sorry, you know, I picked a long example to present. Now this is the correct example. For what values of h is the third vector in the span of the first two vectors. All right, now to answer this question, recall that this rotation means the set of all possible linear combinations of V1 and V2. Now, for V3 in the span, that means that V3 should be able to written as a linear combination of V1 and V2. Now, to answer the question whether V3 is in the span, we need to solve this equation. Okay. This vector equation is a linear system. The coefficient of x1 is V1, so I put V1. Coefficient of x2 is v2, so I put v2 here. And then right hand side is v3. v3. Now I want to know when this linear system has a solution. Okay, reduce the augmented matrix to epsilon form. Then I got 1, -3, 5, 0, 0, 1, and then 0, 0, h minus 10. After I perform some operations, then I get this matrix. This matrix is not in epsilon form yet. Okay, now one more step. Here, I learn, okay, h is a number. I learn negative h minus 10 times row 2, then plus row 3, then put the result in row 3. Then h minus 10 is gone. I get this matrix. All right, now this matrix is in epsilon form. You see, epsilon form, right? Epsilon form. But in this epsilon form, the bottom non-zero row. Look at the bottom non-zero row. This row is this equation. 0 times x1 plus 0 times x2 is equal to 1. But this equation is never be true. So the linear system has no solution for any h. Actually, the conclusion is, okay, now conclusion. Because of the second row, conclusion. V3 is not in the span by these two vectors. These two vectors span a plane in 3-dimensional space. V3, this vector is not on the plane for any h, actually. Yeah, for any h. Okay, this is the first question, similar to the homework. Now, second question. B. For what values of h is the set of these three vectors linearly dependent? All right. To answer this question, we need to go back to the definition. Okay, linearly dependent set. What that means? Go back to the definition. That means that we need to solve this vector equation. If the vector equation has non-zero solution, then the set is linearly dependent. Solve this vector equation. Okay, it is a linear system. Augmented matrix is first column is V1, 1, -3, 2. Second column is V2. Third column H. Then right hand side. The linear system is homogeneous. It always has a solution. Now, let me reduce the augmented matrix. After I perform some operations, then I get this matrix. 0, 0, 1, 0. Then 0, 0, h minus 10, 0. Not in epsilon form yet. Okay, now let me eliminate this number. H is a number. H minus 10 is a number. Let me eliminate that number. Negative h minus 10 times row 2 plus row 3. Put the result in row 3. Okay, now then this number is gone. 0, 0, 0, 1, 0, then 0, 0, 0, 0. It turns out that x2, this unknown, is free because second column contains no previous number, so free. Whenever a homogeneous linear system has a free variable, the system has infinitely many solutions. So therefore, conclusion is this vector equation has non-trivial solution. Okay. Actually, because of low h, for any h, this vector equation has non-trivial solution. So conclusion is the set is linearly dependent for any h, for any h. Yeah. Question C. Now we know that the set is linearly dependent. Phi 1 dependent relation among the free vectors. How to answer this question? That means that we need to find one solution to this vector equation. Okay, now here, this is an epsilon form. One more step to reduce the epsilon form into reduced epsilon form. One more step. Okay, now solution. Epsilon form, we got it from part B. 0, 1, 0, 0, 0, 0, 0. Now negative 5 times row 2 add to row 1. Then the resulting matrix is in reduced epsilon form. Reduced epsilon form. To find the general solution, rewrite this augmented matrix in equations. First row is x1 minus 3 x2. 0 times x3 is equal to 0. Second row, x3 is 0. And then the third row, 0 is 0. All right, now general solution. Solve the basic variable. Yeah, basic. Solve basic variables in terms of the free variables. Free variable is x2. So x1 is 3. X2. X3 always 0. What is x2? Arbitrary. General solution. Now the question is phi 1 dependent relation. That means that let me take one solution. Say, for example, x2 is 1. Then we have one solution. x1 is 3. x3 always 0. Therefore, one dependent relation is plug in the solution in this vector equation. X1 is 3 times V1 plus X2 1 times V2, and then plus X3 0 times V3 is 0. Yeah. This equation is one dependent relation. Done. 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 One more example about section 1.7. One more example. How to answer the following questions? The following question. Okay. Example number 2. How many pivot columns mass a 7x5 matrix have if its columns, one column of a matrix is a vector. If its columns are linearly independent. Okay. Okay. Explain your answer. Why? Okay. Now solution. Okay. Okay. Let A be this 7x5 matrix. This matrix has 5 columns. Let me denote the first column by A1, second column by A2, third column by A3, A4, and A5. Each column has 7 entries. So each column is a vector in R07, the 7-dimensional space. Okay, let A be this matrix. Now we know that the columns are linearly independent. Okay. Now the columns are linearly independent. Now X1, by definition, X2 times A2, X3, A3, X4, A4, X5, A5 is 0. Columns are linearly independent. By definition, that means that this vector equation has only 0 solution. Has only 0 trivial solution. This vector equation actually is a linear system. Okay, this vector equation is a linear system. That is the linear system. Augmented matrix is A. Right hand side 0. A1, A2, A3, A4, A5, 0. Has only 0 solution. When a homogeneous linear system has just 0 solution, anyone can tell me? This linear system has just 0 solution. That means that, do you agree with me? All the variables are basic variables. low free variable. Do you agree? Okay. The linear system has just zero solution. Then low free variable. That means that each column is a basic column. That means each column of coefficient matrix, not of the augmented matrix. The coefficient matrix, yeah, here, this part. Each column is a basic column. Is a basic column. It's a basic column. So I have answered the question. How many pivot columns this matrix have? How many? 5. Conclusion is 5. Conclusion. Yeah. This matrix A. Yeah. A means this matrix has 5 pivot columns. Yeah, done. Yeah. Yeah. Okay, I finished section 1.7 with this example 2. Now let's turn to the second topic. Matrix operations. Okay, now let me introduce you formulas. Okay. Topic 2. Matrix operations. Okay, first, let me introduce you how to perform a matrix plus a matrix. Suppose A and B are matrices of the same size. A matrix plus a matrix. We assume those two matrices have the same size. Otherwise, summation, subtraction, they are not computable. Okay. Okay. Now, precisely, let me let A be, say, m by n. A11, A12, m by n. So A1n. A21, A22, A2n. And m by n. So AM1, AM2, AMN. Matrix B, same size. B11, B12, B1n, B21, 22, 2n. BM1, M2, MN. Okay, now summation. Okay, summation. A plus B. Okay. Okay. Let me also write these two matrices in columns. First column A1, second column A2, and last column AN. B, B1, B2, BN. Now I define A plus B. A plus B is first column plus first column. Second column plus second column, and so on. One column is a vector, this vector plus this vector at the corresponding entries. So in detail, it is A plus B, 1, 1 entry plus 1, 1 entry, 1, 2 entry plus 1, 2 entry, and so on at the corresponding entries. As 2, 1 entry plus 2, 1 entry, 2, 2 entry plus 2, 2 entry, 2n plus 2n entry. Yeah. At the corresponding entries. M2, M2, Mn, Mn. Yeah. So A plus B is a new matrix by adding corresponding entries. Now, how about A minus B? Okay, very similar. A minus B is the first column of A minus the first column of B. Second column minus second column. The last column minus the last column. Right? That means subtract the corresponding entries. This is A plus B and A minus B. Now the second operation. A scalar times a matrix. Okay. C is a number times a matrix. In columns, it is the number times first column. One column is a matrix, is a vector. A number times a vector is the number times all the entries of the vector. C times second column. C times last column. Yeah. In detail, it is C times all the entries of matrix A. C21, C22, C2n, C, M1, M2, CMN. Yeah. This is a number times a matrix. All right, a matrix plus a matrix minus a matrix, a number times a matrix. The formulas are straightforward. Now, let me define a matrix times a matrix. Okay. Okay. A matrix times a matrix. A matrix multiplication. All right. Here, definition. Okay. All right. If matrix A is now is an M by N matrix. Pay attention now, okay? And B an M by say P matrix. Yeah. Pay attention. This N and this N should agree. This N is the number of columns of A. This N is the number of rows of B. The number of A, the number of columns of matrix A should be equal to the number of the rows of matrix B. Otherwise, we cannot perform A times B. Okay, pay attention. Okay. All right. Then the product A times B is an M by P matrix. Yeah. The middle n is cancelled. M by n times n by p. The result is m by p. Okay. The formula. There are two formulas. Formula 1 to compute A times B. Formula number 1. Okay. A times B. Let me split matrix B into columns. First column, B1, B2. How many columns the matrix B has from this size? N by P, P columns, BP. A times B, this matrix is A times B1. We know how to compute a matrix times a vector. That is in chapter 1. A times B2. A times BP. Yeah. Formula 1. Formula 1. Right. So A times B, it is a matrix. The columns of the matrix is A times B1, A times B2, A times BP. All right. Yeah. Let me put a remark again. These are the columns of A times B. A times B. Yeah, the formula 1. A times B is defined to be A times each column of matrix B. Now, second formula. Second formula is called row column formula. Okay, next page. Okay, formula 2. Formula number 2. A times B is a matrix. A times B is a matrix. This matrix, the ij entry is equal to row I of matrix A times column J of matrix B. Second formula. A times B is a matrix. The ij entry is row I of A times column J of B. In detail, row I of matrix A is A row I. The first entry is AI1. Second entry, AI2. How many entries in each row? We assume matrix A is M by N, and matrix B is N by P. So each row has N entries, AIN. This is a row I. Now column J of B. B1J, the first entry. B2J. How many entries? N entries. BNJ. Yeah. Hey, now this row times this column, its meaning is the sum of the products of the corresponding entries. So AI1 first entry times B1J first entry of this column plus AI2 second entry times second entry, and so on. Make a sum of the products AIN, B, and J. second formula, okay, to compute a matrix times a matrix. Yeah. Okay, let me show you example. One example, several examples actually, about how to use these formulas to compute a matrix times a matrix. Okay, take a look. Yeah. Example 1. Let matrix A be 4, 2, -3, 0, 3, 5. It is the size is 3 by 2. Okay. Matrix B is 1, 3, 4, -1. The size is 2 by 2. Number of columns of matrix A is equal to number of rows of matrix B. A times B is computable. Okay. All right. Now the question is, compute A times B by formulas number 1 and number 2, respectively. Okay, respectively. Okay, now solution. Now by formula 1 first. Formula number 1. Formula number 1 says that a matrix times a matrix is the first matrix times the columns of the second matrix. Formula 1. Okay. Okay. A times B. Let me split B into columns. 2 columns. Okay. So by formula, it is A times first column, A times second column. Okay. Where A times the first column is this is A, 4, 3, 3, -2, 0, 5. First column of matrix B is 1, 4. Recall the formula to compute a matrix times a vector in chapter 1. A matrix times a vector is a vector. The vector is a linear combination of the columns of the matrix. So it is a first column times 1. And then 4 times second column. Formula for a matrix times a vector. Okay, now this is 1 times all entries, 4 times all the entries, then add them together. So it is 4 minus 8, so -4. -3 plus 4 times 0, -3. 3 plus 4 times 5, 23. Yeah. A times B1. Now let me compute A times B2. A times B2. A times B2. It is A. Matrix A. B2 second column of matrix B. 3 -1. A matrix times a vector is a vector. The vector is a linear combination of the columns of the matrix. So 3 times first column. Then plus -1 times second column. So 3 times 4 plus 2, 14. 3 times -3 plus 0, -9. 3 times 3, 9, minus 5, 4. Yeah. Okay, so A times B is A times B1. A times B2. Okay, plug in the result. Okay, A times B1, -4, -3, 23. -4, -3, 23. First column. Now second column, A times B2, 14. 9, 4. Yeah. This matrix is the result of A times B. This is a formula 1. But I usually I like to use formula 2. Formula 2. Formula 2. This formula, the book gives it a name. Call it row column. Ooh. Okay. All right, now A times B. Recall that A is what is size? 3 by 2. B is 2 by 2. Therefore, the result should be 3 by 2. Okay, 3 by 2. All right, let me write down matrix A in detail. Matrix B in detail. 1, 3, 4. -1. Okay, yeah. All right. The result of the product should be a 3 by 2 matrix. The 1-1 entry. How to get the 1-1 entry? By row column formula. 1-1 entry should be row 1 times column 1. So therefore, it is 4 times 1 plus -2 times 4. 1-1 entry. 1-2 entry should be 1-2 entry, row 1 times column 2. So it is 4 times 3 plus -2 times -1. 1-2 entry. Now, how about 2-1 entry? 2-1 entry is row 2 times column 1. So it is -3 times 1 plus 0 times 4. 2-2 entry, row 2 times column 2. -3, 3 plus 0 times -1. Yeah. Now, the 3-1 entry. 3-1 entry is row 3 times column 1. So the result is number 3 times number 1 plus 5 times 4. 2-2 entry, row 3-2 entry, row 3 times column 2. So 3 plus 5 -1. So the answer is okay. Now calculator 4 minus 8 -4. Here 12 plus 2 -2 times -1 plus 2 14. -3 -9 plus 0, and then 3 20 23. 9 minus 5 4. Yeah, done. This is the result from formula 2. Usually I use formula 2 to compute a matrix times a matrix. Now the next example, the matrix product is not computable. Take a look. Example number 2. Let matrix A be 2, -5, 0, -1, 3, 4, 6, -A, -7. The size of this matrix is 4 by 3. 4 rows, 3 columns. Now, how about matrix B? 4, 7, -6, 1. Now find A times B. Pay attention. Matrix B is just 2 by 2. The number of columns of matrix A is not equal to the number of the rows. Let me try to find the product by row column formula solution. Okay. Let me try. Okay, A times B. Let me try. Matrix A. Let me copy. By row column formula, the 1 entry should be row 1 times column 1. Let me try. 2 times 4, plus -5 times 7, and then plus 0 times nothing. How about 2-1 entry? 2-1 entry here should be row 2 times column 1. -1 times 4, -1 times 4, plus 3 times 7, plus -4 times nothing. Not commutable. So the answer is A times B is not defined or not computable. Okay, not computable. That is the answer. Second example, example number 3. Example number 3. And let me adopt the matrix AB from the previous example, but I make some change on B. Let A be 2, 5, -5, 0, 3, 4, 6, -8, 7, 0, 9. Okay. Okay. Let me add 1 row to B so that A times B is computable. Okay. Let me add a row. 3, 2. Say okay. 3, 2. Now have a check with the size. This is a 4 by 3, and this is a 3 by 2. Now, the number of columns in A matches the number of the rows in B. So A times B, computable. Right, now the question is, find the entries in the second row of A times B. Okay, now solution. We are only required to find the second row. Okay, we don't need to find the other rows. Okay, now A times B 2. Yeah. This is A. Now B. Okay, I only need to find the second row. The result, the size of A times B should be, let me cancel the middle 3. The size is 4 by 2. Yeah, 4 by 2. A times B, the size is 4 by 2 matrix. Okay, now I don't need to compute first row. First row, let me put star. Star means any number. Second row. Okay, now second row. Row 2, 1 entry times column 1. So I get -1 times 4. It is -4 plus 3 times 7, 21. So so it is -4 plus 21, 17. And then -4 times 3, -12. So 5, right? You agree? 5 here. 2 entry, row 2 times column 2. -1 times -6, 6. 3 times 1, 3. So 9. -4 times 2, -8. So 1. Done. Okay, third row, 4 row. We don't need to compute. So done. The entries in the second row of A times B is 5, 1. Okay. All right, now let me make a summary. Okay. Make a remark. Okay, remark. Remarks. In general, the following are always true. The J column of A times B by formula 1, A times B is A times each column of B. So the J column is A times the J column of matrix B. B, the ith row of A times B from example 3, we can see that it is row I of A times the whole matrix B. Yeah. Row I times the whole matrix B. Yeah. More examples about a matrix times a matrix. Okay. Yes. Yeah. Matrix times matrix. The formulas can confuse some students. Okay. Example number 4. Okay, now take a look here. Let A is a matrix with only one row. 4, 1, 3. Yeah, the size of this matrix is 1 by 3. Okay, now B, this matrix has only one column. 2, 3. The size is 1 by 3. 1 by 3. And this is a 3 by 1. Okay, now the question is 5 A times B. A times B is computable because the middle this number of columns, number of rows, they match commutable. Okay. So the result is 1 by 1 matrix. And B times A. B times A. B, the number of columns is 1. A, the number of rows is 1. So match, commutable. Okay, commutable. All right, now let me try. Okay. Solution. A times B. The result should be a 1 by 1 matrix. Okay, 1 by 1 matrix. Let me copy the matrix A. Matrix B. The result is 1 by 1. Okay, only one entry. The entry is row 1 times column 1 by row column formula. So it is 4 times 2 plus -1 times 1 plus 3 times 3. Now calculator. 8 minus 1, 7 plus 9. So 16. Yeah, 1 by 1 matrix. Yeah, this is the result of this A times this B. Now, how about B times A? Okay. B times A. Let me write down B. B 2, 1, 3. 3 by 1. A 4, -1, 3. 1 by 3. A commutable. Okay. This is a 3 by 1. 1 by 3. Then the result is 3 by 3. Cancel the middle one. Okay. 3 by 3. Okay. Now the result is 3 by 3. Okay. 3 by 3. Okay. The 1 by entry by row column formula is row 1 times column 1. That is 2 times 4. That's it. 2 times 4. That's it. 1, 2 entry. Row 1 times column 2. 2 times -1. 1, 3 entry. Row 1 column 2. Column 3. 2 times 3. 2, 1 entry. Row 2 times column 1. 1 times 4. 2, 2 entry. Row 2 column 2. And then row 2 column 3. Here 3, 1. Row 3 times column 1. Row 3 times column 2. Row 3 times column 3. So the answer is this. 8, -2. Here 6, 4, -1, 3. Here 12, -3, 9. Yeah, done. Hey, from this example, done. Okay. From this example, we can see that a matrix times a matrix usually is not equal to A times B. Usually is not equal to B times A. This is true in matrix product in general. It doesn't like numbers. Yeah, number. 7 times A, of course, is equal to A times 7. But for matrices, usually matrix multiplication doesn't commute. You cannot switch. Okay. Okay. One more example. One more example. Say here. Example number 5. Let A be 5, 1, 3, -2. 2 by 2. B is 2, 0, 4, 3, also 2 by 2. Now find A times B and B times A. Solution. A times B. 2 by 2 times 2 by 2. Cancel the middle 2. So the result is still 2 by 2. By row column formula, 1 entry, row 1 times column 1. So again, 5 times 2, 10, plus 1 times 4, 14. 1, 2 entry, row 1, column 1, 5 times 0, plus 1 times 3, number 3. 2, 1 entry, row 2, column 1, 3 times 2, 6, minus 8, negative 2. And then 2, 2, row 2, column 2, negative 6. All right. Now, how about B times A? Also computable. Okay. B, 2, 0, 4, 3. A, 5, 1, 3, 2. The result should be 2 by 2. The size. 1 entry, row 1, column 1, 2 times 5, 10. 10. 1, 2, row 1, column 2, 2. 2, 1, row 2, column 1, 4 times 5, 20. 3 times 3, 9, 29. And then 2, 2, row 2, column 2, 4 times 1, 4. 3 times negative 2, 6. Negative 2. Yeah. Again, from this example, we can see that A times B not equal to B times A. This is true in general for a matrix times a matrix. We call this property matrix multiplication doesn't commute.